Yeah, let's get started today's class. Okay, so in the previous class, we learned about the always statement in system value, right? So I mentioned that we frequently use always statement, and then you need to you need to memorize the definition of this always statement. Okay, so actually this is the basic definition. So actually, as I mentioned, the system value is the superset of the value. So it was, it, it has been developed from value, okay? So actually, this original definition of always statement is like this. So there is a sensitivity list, and then if the condition of this sensitivity list is met, so it's true. So it's not kind of true or false because the sensitivity list just the lists some changed signal. So it monitors the changes of signals. Okay. So if the signals in this sensitivity list change it, then the always statement will be executed. So it means that the statement inside of always statement will be executed. Okay? But actually for system value, you can just know the three different kinds of the always statement. So for the combinational logic, you can use always underbar com, okay? And then for the sequential logic, the normal sequential logic, so you can use the always underbar ff, and then for latch, so in order to generate latch, then we can use always underbar latch, okay? So we will learn about the latch this class. Okay, so we learned about some other statement like if else. Okay, I believe you can easily understand the if else statement because we frequently use this if else statement in Python, also in C or C++, right? And then actually, but you need to know that so actually in system value, just so we use this system value in order to implement real hardware. So which means that your code needs to be synthesized into real hardware. So which means that actually when we use the if else statement, then you need to define all possible conditions for this if else. Okay, so it is recommended to use else always for combinational logic. Okay, so actually, in a sequential logic, we don't need to use you don't need to define all possible conditions for this condition in sequential logic. But for combinational logic, so we need to define all possible conditions for if else also case statement. If not, then I said the latch will be generated. And I said this is bug. Okay, so we need to avoid bug. Okay, so it's very critical for the also, it's very critical for software design. Also, it's very critical for hardware design. Okay? But for hardware design, the bulb is extremely more critical, right? Because software we can fix software easily. So that software, and if bugs are found, then we can just catch bugs, right? So we can fix our code. But hardware is different. The hardware is real BSI product, right? So it's a real chip, right? So it's very difficult. It's difficult to fix the circuit inside of chip. So actually it's not possible. So actually it is already fabricated. And actually, it's a silicon, right? It's a kind of stone. Okay? We cannot modify. We cannot modify this stone material, right? So we also learned about the case, okay, and then based on the if else or case statement, we can implement the multiplexer, right? So actually, so I recommend to use the ternary operator. So actually, because if you use the ternary operator, then we can easily implement two-to-one multiplexer using only one line of statement. Okay, but for the both one multiplexer, then we can use the case statement, but I also explained about the synthesis primitive. Okay, so that is the special command for the synthesis. So actually, this is command actually. So actually, during the simulation, this synthesis primitive will not be translated. So will not be reflected to the synthesis no, simulation two. But for the synthesis, then synthesis two read the synthesis primitive, then the synthesis two will generate the desired hardware based on this condition. Okay, so kind of special commands for synthesis tool. Okay. Okay. So let's learn about the delays in system value. So actually, we learned about the delays in combinational logic, and then so you need to know that every circuit exhibit delay. So it's a real circuit. Actually, every system, every system exhibit delays actually. So right. So input is given, then output is generated, but after some time, right? Because in real world, the systems work in real world, and then so the real world. So we need to consider the time, right? So we need to also consider the delays in our circuits or hardware, right? So we can represent delays in system value. How? So actually, I already explained about this timing specification, right? So we can define a timing specification. Okay. So we already did the first lab assignment. So okay. So and then if you read the test bench code, then you can find this number. Okay, also time scale. So I already explained about this time scale. Okay. So it's a 1 nanosecond, and then this is the precision. So actually the first this scale the represent the time unit of this number. Okay, so I mentioned that this is the 1 nanosecond. So which means that is 10. Number 10 represents the 10 nanosecond because the unit of this time scale is nanosecond. Then what is this picosecond? This 1 picosecond, so after this time unit, so this number represents the resolution. The resolution that can be used in the system value module. What does that mean? What is the resolution? So, for example, if our resolution is the time resolution is my writing is not good. So if the time resolution is 1 second, right? Then can we represent 1.5 second. So actually, if we just so this is related to the some hardware. Okay, so so let us assume that the hardware can detect some this time resolution, and then the time resolution is 1 second, but we want represent 1.5 seconds. So, but it is not possible. So it is because the resolution of the time scale is 1 nanosecond. So which means that we can represent 1 second, 1 second, 2 seconds, 3 seconds, like this. But 1.5 seconds is not cannot be represented. Okay, because we just define the resolution of this time scale as the 1 second. So in order to use this 1.5 second resolution, then we need to set this time scale at the uh, 0.1 second or 100 millisecond. Okay, so resolution just represent the minimum resolution that can be used in this system value module. So in this example, the time resolution is 1 picosecond, right? So which means that it is possible. So we can just use this number like the 10.001. Okay. So 10.001 is nanosecond is it's a 10,001 picosecond, right? So this is the 10,001 picosecond. So it is possible. So because we just set the resolution of this time scale as the 1 picosecond, so this is possible. But 10.0001, this is not possible. So this because the minimum resolution is 1 picosecond. So just this is it just define the minimum resolution of time scale. Okay. And then so using the time scale, then we can just define the time unit and then time resolution of system value module, and then so you can find some representation of delay. So in this test bench, then so initially the A is set as the 0, and then I don't know what's this is 0. So and then after that you can find some number, and then so you can find this sharp symbol, and then after that you can find the number, and then this number represents the delay. Okay, so simply it represents after 10 nanosecond. So if this is delay, so it means that in 10 nanosecond or after 10 nanosecond, because the time unit is nanosecond, then A will become 1 bit 0, and then B will be also 1 bit 0. Okay, right? Also, you can find some another delay signal here. So in system value code, we can also represent the timing specification. So like delay, okay, like this. Okay, let's see another example. So you can find the multiple assigned statements here, and then you can find the delay here. Okay, so in order to use time delays in assigned statement, then you can write the delay after this assigned statement. Then what is the definition of this delay, time delay in assigned statement? So what is the definition of assigned statement? So you can just understand the definition of assigned statement like this. So this is the right hand side signals, okay? And then if one of one of these signal values change, then the left-hand signals are updated. Okay, so assign statements will be executed if these right-hand signals are changed, right? So we can understand the assign statement like this. If the right-hand side signals are not changed, then assign statement will not be executed. Okay, so A, B, C. So there are three signals here. Then so this, if the A or B or C are changed, then the left-hand signals, so this AB, BB, or CB will be updated. So it's calculated. But we can find the delays. So it means if A, B, C are changed, then after, so in 1 nanosecond, after 1 nanosecond, this will be reflected. The changed value will be reflected to the left-hand side signals. So do you understand? So assign statement will be executed when these signals are changed. These signals are changed, but the output will be reflected after this time delay. Okay, so you can understand the time delay of uh, uh, in the assign statement like this. Okay, okay. Then so, but you need to also remember that delays are for simulation only. So I said that you need to distinguish simulation and synthesis, the real hardware. Okay, so actually this delay will not be reflected to the synthesized hardware. So you need to remember this. So sometimes the students can think that, oh, we can make any hardware using a system value. So which means uh, we can just implement some delays. So we can just represent delays of hardware in system value. Then you can think that, oh, then synthesize the hardware will have the defined timing delay, the timing specification defined in this code. But it's not true. Actually, delays timing specification in system value cannot be implemented, cannot be synthesized into hardware. It's simulation only. Okay? 이걸 저도 배울 때 헷갈렸어요. So even though we said, oh, this delay, so you know this is the NOT gate, right? So this is NOT gate. So and then we said, oh, the delay of this NOT gate is 1 nanosecond. So then if this logic is synthesized, the NOT gate will be synthesized. The NOT gate will be implemented like this. So it's A, NOT gate, and AB, right? But the delay of is synthesized NOT gate is not 1 nanosecond. Okay? It's just a simulation. The delay of is NOT gate is determined by real circuit implementation, not this value. Okay? So actually the verification components such as TSMC or Samsung. So they're those very famous top top fab companies. So they can just implement. They can fabricate the real chip, okay, real silicon devices. So they provide this circuit, okay. So which means that they also provide the inverter circuit based on their CMOS technology, okay. But the delay of this inverter circuit is determined by the real circuit developed by those companies, TSMC or Samsung, okay? So fabrication companies, right? So we cannot define. So actually we cannot define real timing specification of the hardware, okay? Those real timing specification of hardware will be defined by circuit implementation based on the CMOS technology. Then why do we need to learn about the delays in system value? So it's because we can just understand how the combination logic includes the delays. Okay. Also, after synthesis, so actually these companies provide some the circuit libraries. Okay. So, and the circuit libraries are combined in the synthesized circuit, then we also need to measure delays. Okay, so we will learn about this timing specification later. But when this after synthesis, then the timing delay information will be included in this system value statement. Okay, then we can just measure the timing delay of this circuit using simulation. Okay, so just remember that delays are just simulation only. Okay, they do not determine the delay of your project. It's just a simulation. Okay, but we need to understand how the delays are reflected in system. Okay, because we can use this information after synthesis. Okay, so let's see let's see the example of this code. So you can find multiple assignment statement, right? Assign statement here. Then, so in this example, so you can find that there are 3 input ports and then 1 output port, and then also you can find the several internal nodes. Okay, so A, B, C determine the A, B, 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 C, B, and then also the internal nodes N1, N2, N3 are determined by A, B, some internal nodes A, B, B, C, B, and the input signals. Okay, and then finally the output signals are ordered for the internal nodes N1, N2, N3. Okay. Then how delays are reflected? Okay, so when I explained about the delay in assign statement, I mentioned that assign statement will be executed if the right hand signals are changed, and then the output will be reflected after this delay. Okay, so based on this definition, then we can just estimate the waveform. So this is the waveform of this signal. Okay, so in the waveform you can find some signals here, and then also you can in the x-axis you can find the time from 0 to 10. Okay, so this is the input signals A, B, C, and then you can find that initially the ABC signals are determined. So in simulation, in a system value simulation, the initial value of A, B, C is actually don't care. Okay, don't care. So this is the initial value. Okay. And then we can define the ABC value like A is 0, B is 0, and C is 0 initially. So I mentioned two initial. Initially, it is X, but when simulation starts, then we can initialize these ABC values as 0. So I just use two initialized. Well, so what is different? Even so, actually the system value used some how can I say? So actually the system value determines the change of signals like the some sequential change. So it means it's not real time specification. Okay. So it means actually the system value just so actually this is the t is 0 and then this is the t is 0, right? So actually, so it is because I initially ABC is don't care and then it will be initialized as 0, 0, 0. So actually, if we just consider the time scale, then actually at time 0, ABC is x, and then at time 0, ABC will be 0, right? But in system variable, there is a very small time gap between these two events. Okay, so so you can just understand that the system variable just uh, determines the order of signals. Okay, order of change of signals. Okay, so it means even though at the same t equals 0, so actually the time is the same, but this is the former event, this is the following event. Okay, so this is the later event, and the system value would just think that oh, there is very small delay. Okay, and then this delay is called the delta delay. Oops. Okay. So delta, so like this limit time equals 0 or delta t is 0. Okay. So actually in mathematics, we can also define the delta delay like this. So we can just uh, we can just make the time gap as 0 using this limit operation. Okay. So actually, in real mathematics, this delta t is actually 0. It represents 0, but we can just know that delta t has some value. It's a very, very small value. Okay, it's a limit, but we can just make the order of these two events. So system value, even though this time is the same, t equals 0 and t equals 0, system value would just use the some delta delay concept. So system value just add some small delta delay between these two events. Okay. Okay. So you can just understand this delta delay concept like this. So limit delta t equal 0. So then how can we explain the delay operation? So as you can see, this is A, B, C. So actually initially these are all don't cares. Okay, X, and then at t equals 0, it is changed to 0, 0, 0. If you see this waveform, then you can find that the small the line here, the vertical line here. So it represents it was x, but at time t0, it is changed to the 0. Okay, so at this t equals 0, then it is changed to the x is 0, x to 0, x to 0. Okay, so because the right hand signals are changed at t equal 0, then this will be executed, right? This assign statement will be executed because the values are changing, right? So not operation will be executed, but the output is reflected after 1 nanosecond. So if you see the waveform, then you can find that A, B, 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 and C, B is here. So actually, if you see this waveform, you can find that this is the X. Okay, it's a gray. Actually, this is gray color. So you can find that these signals are blue color. Okay, but actually, during this 1 nanosecond, A, B, 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 C, B is X. Don't care. And then, so it is because it was initially don't care, right? And then, because the ABC is changed from don't care to 0, but at the 1 nanosecond, the output will be reflected. Okay? You understand? So, A, B, B, A, B, 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 C, B will become, what's this? 1, 1, 1, 1, 1, 1, but after 1 nanosecond. So, then you can find that for this second assignment, you can find the A, B, 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 C, B, right? So the value is changed. So value is changed from x don't care to 1 at time t equal 1, right? Then this assign statement will be executed. Okay, you understand? So this will be executed. So, and after 2 nanoseconds. So, after 2 nanoseconds, and 1 will become 1. Okay, so you can find the x for first 3 nanoseconds for this and 1. Okay, so at this point, it's changed, so it is reflected after 2 nanoseconds. Then how about the A, B, B, and C, B? Okay, so this assignment is also mentioned that, oh, this is A, B, B, and C, B, but after 2 nanoseconds. So actually, you can find that the A is changed at t equal 0, and then BB and CB, the value of BB and CB will be changed at t equal 1, t equal 1, right? Because, so, you know, so A, B, C is changed at t equal 0, then so it is A, B, 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 C, B will be changed at t equal 1. Then how can you calculate? So, because, but after 2 nanoseconds, so because in this assignment, so this assignment, right? For this assignment, one of the right-hand signals are changed at t equal 0, right? Right? Because A is changed. So it will be executed. Understand? It will be executed. So at t equals 0, then this AND gate will be executed. So what is the value? The value is 0, and actually it's x at t equals 0. So don't care and don't care. What is the value? What is the output? Output is 0. Why? This is because this is is a 0. Is it because this is AND gate, right? Right? So, but this output will be reflected after 2 nanoseconds. So that's why if we see the N2, then N2 will be 0 at time at t equal 2. Do you understand? So, at t equal 1, dB and CB will be changed. Then this assigned statement will be also computed. Okay, but still A is 0, so the output value is the same. So that's why the waveform is 0 continuously. So actually for this assignment, the N2 or N2 is the same. So because the A is changed at t equals 0, and then BB and CB are changed at t equals 1, so it is computed twice at t equals 0 and then at t equals 1. This statement will be executed twice. Okay, so that's why you can find that the N1 is stabilized, becomes 1 after 3 nanoseconds, right? But N2 and N3 becomes 0 after 2 nanoseconds. Okay, so you can just understand. So, but the assigned state 1, then the right-hand signals are changed. That is executed. Okay, actually for the N2 and N3, it is executed at t equals 0, and then it will also executed at t equal 1. Okay, then we can calculate like this, and then finally the N1, so 2, and then finally then y equal N1, N2, N3. Okay, so N1 is changed at this point, and N2 is changed at this point, right? So actually it's a t equal 2, and then it's a t equal 3, right? So at t equal 2, then this will be executed, right? Because the N2 and N3 values are changed at t equal 2. But why is x still x? So at this point, N1 is x, N1 is x, N1 equal x, and 2 equal, what is this value? 0. Then N3 is 0. Okay. So we need to calculate the x or 0 or 0. So what is the value? What is the output? Output is still x. We don't know because we don't know this value. So if this value is 1, then it will become 1, right? And then if this value is 0, then it will become 0. So actually, at this point, so we don't know. We don't know exact output value. So it's still X. We don't know. Then at t equal 3, right? The t equal 3, and 1 becomes 1. Then and 2 is still 0, and 3 is still 0. So because we know the exact value of n1 at t equal 3, the time is 3, then what is this value? This value will be 1. So y will become 1. But after 4 nanoseconds. So this output value will be reflected after 4 nanoseconds. So that is 3, and then after 4 nanoseconds. So at time t equal 7, then y becomes 1. But before that, it is still not here, x. We don't know. So we can calculate we can understand the delay of the system value like this. Okay. So it may be a little bit tricky because so actually this is the system value is designed for hardware. So that's why so I explained that so some signals are changing, then output is changing. Some signals are changing at time t equals 0 or t equals 1, t equals 3, like this. I explained like this, right? So in normal programming languages, we can just understand that these statements are executed sequentially from top to bottom. Okay, so like this statement is executed, one state 2 is executed 3, and then blah blah blah. Okay, so all statements are executed sequentially in normal programming languages, but the system Verilog or other HDLs, we need to consider time, right? This is very important. So we need to, and then also the definition is different. The definition is that in the statement, if a certain values are changed, then this statement will be executed. So just to remember this. So even though this is a programming language, but the concept is different. Do you understand? So that's why the normal programming languages are easier. Okay, in the normal programming languages, then we can just think that the command or statements are just executed from top to bottom sequentially. So there can be some functions or the function calls or procedure calls, but it's okay. Just executed from top to bottom, and that's it. But in the system value, there is some condition, a condition of execution. The condition is just that if signals are changing, then statement will be executed. Okay, so if this a value is changed at this point, then this assignment statement will be executed also. Okay, so it depends on this right-handed signals. So we can just understand the always statement like this because the always statement also includes the sensitivity list. Okay, so which means if the sensitivity list are the values, the signals in sensitivity list are changed, then always statement will be executed, right? So in the assign statement, so actually A, B, C are signals in sensitivity list. Okay. Okay. So this is the main difference. Main difference between the normal programming languages and then hardware description languages. Okay? So I hope you can understand. You can understand this difference. Okay. So it's a little bit. So if you are familiar with the programming languages, then it will be a little bit tricky. But try to understand some behavior of system value like the real hardware behavior. And then in order to reflect the real hardware behavior, the system value includes the concept of time. Okay. Okay, so let's go to new topic. Sequential logic. So, so actually at this point, we learned about the combinational logic. So what is the definition of combinational logic? The definition of combinational logic is that output signals are just determined by input signals. This is the definition of combinational logic. So then from now, we will learn about the sequential logic. Actually, we learned about the definition of sequential logic. So what is the definition? Sequential logic has memory and then outputs determined by previous and current value. So previous means that actually the emit state. So combinational logic is a memoryless. So it means that the output values are just determined by input values only in current input, but sequential logic has memory, okay? And then it means that it has states. So output values are determined by current input and this state, previous input. So actually, because the input determine the state, so that's why it is written like the output determined by previous and the current value. But it means that it's state of this system. So what is state elements? So how can we understand the state like this? So this is the example. So if you Google a state of matter, then you can find this diagram, this figure. Okay, so it's familiar. So those are states of matter. So there are three different states of every matter. Okay, every material. So liquid and solid and gas. So this is the, for example, so this is the liquid state. And if the heat is removed, the heat energy is removed from this liquid state, then it goes to solid state. So which means this is the output. The output of this material, so it's a solid state. This solid state is determined by current state, the liquid, and some input. So reduction of heat energy is a freezing. Then so this is the reverse reaction. So if the heat energy is given to the solid, then it goes to the liquid state. So we can know the output. The output of this system, so it is also system. Output of this system is determined by input and current state. Okay, and then actually the current state, the solid state or liquid state or gas state, is actually determined by previous input history, right? Like heat energy is given or heat energy is reduced. So we can understand some sequential logic like this. Okay, so we can understand the state of a system like this. So actually, every system, so most systems include state, right? So this is the system of our nature, right? So our nature also includes the states of material or matters. Okay, so we can understand the state like this. So when we make a system, then we can also define states, and then these states are determined by previous inputs, the input signals actually, right? So we can also define states. So in order to define this state, then the system requires memory element. Okay, so it means the state, the system needs to store state, right? That's why sequential logic includes memory. So if you think about the memory, then you can think like, oh, so it's a DRAM or a flash memory, or how to describe. You can think like this, but this memory is different. It's a different from these kind of memory components like DRAM, flash memory. So just ignore these memory components. So memory means that. So in the logic, the memory means that states are stored in a system, right? So in order to store these states, then system requires the memory, okay? Because if we do not have memory, then we cannot store this state like liquid. So then actually in a real system, like it's a nature system, if we do not know the current state like liquid, then we don't know the output. Okay, so it's the same. Actually, in order to implement the sequential logic or state logic, then we need to store this state, the current state, okay, in a system. Okay, so it has a memory. So it means the binary signals or electric signals need to be stored inside of a circuit. Okay. So in summary, in order to implement some more complex system, then actually our system requires state. Okay. So it means that the states are determined by the previous history of input signals. But our systems need to store current states to generate some output values. Okay. So in order to store current states, then system requires memory. It means digital signals like electric signals such as voltage level, digital signals need to be stored inside of the circuit or system. Okay? The systems are implemented using circuits. Okay, so it means digital signals or digital values need to be stored inside of circuit. Okay, so those are state elements. Okay, in order to implement the sequential logic, then we need to, so this logic includes the memory. But you can understand that this memory is the short-term memory. It is different from the some other type of memories such as the DRAM or flash memory. So DRAM, actually we use DRAM or flash memory to store our data. Okay? But when we mention memory in this course, then it means the some short-term memory that stores current state. Okay. Okay. Then, so in order to implement this sequential logic, then we need to implement the memory components. It's short-term memory logic using the basic logic gates. Okay, so it means so like the very basic logic gates or very basic combinational logic. So in order to build the sequential logic, then we need to also learn about the basic state elements. Okay, so basic sequential logic blocks. Okay, so we need to learn about the bistable circuit, latch, as a latch, then latch, then flip-flop. So actually, in the digital systems, we normally use T flip-flop, okay, not latch, because I mentioned that in system value, so if latch is generated, it's wrong, right? But we need to understand how latches work. Okay, the some basic concept of a latch in order to understand the T flip-flop. Okay, so I will start from the bistable circuit, and then we will learn about the latch, SR latch, then T latch, and then based on the T latch, we can implement the flip-flop. Okay, this is very important uh, components. Those are very important components. And then actually, our digital system is implemented using combinational logic and deep flip-flops. Okay. Okay, let's start from the bistable circuit. Okay. So first, which circuit is required for implementing? Which circuit is required for storing digital signals? So firstly, we need to think that, so how the electric circuits, how digital circuits can store a certain values, a certain signals. Okay, so we need to store digital signals. Then how? So we can store certain digital signals using serially connected inverters. And then, so if you see this circuit, then you can find that there are two inverters. Two inverters are serially connected, but the output of this inverter is also connected to the input of another inverter, right? This inverter has the feedback loop, okay, from output of this I1 to the input of I2. Then what is the behavior? What is the behavior of this circuit? So if you see this circuit, then you can find that this circuit does not have any inputs. Okay, but this output is just feedback to the input of this I2. Okay, and then there are two outputs, Q and Q bar. But this is a memory. This is a memory logic. We can store digital value. How? If the Q equal 1, so this is the digital signal, so which means that we can just use the one of values. So that is this is the advantage of digital system. So because the values are very simple, signals are very simple. So let us assume that Q is 1. Okay, so this Q is 1, and then 1 is given to the input of I2. Okay, so this is 1. Then what is the value? This node becomes 0 because this is inverter. So Q bar is 0, and then Q bar is also the input of I1, inverter 1. Okay, so 0. So this is 1. So what can you observe? If a certain signal value is decided in this circuit, like a Q equal 1, then this is 1, and this is 0, and this is 1 continuously. And then, this is the driver. Okay, this is the driver. So these circuits, inverters are driving 0 for this Q bar, and then 1 for this Q continuously. So signal values are maintained. It means it's stored. Signal values, the digital signals can be stored. How about the Q equal 0? If the Q equals 0, it's a 0, then it's a 0, and then, simply this is 1. Q bar is 1. And then also the Q is 0. So we can think about the two different values, Q equal 0, 1, or Q equal 0. Then in this circuit, in this bistable circuit, the output values. So actually the values are stored. It's maintained continuously. Okay, so after a very long time, Q is still 1. Okay, if the initial value is 0, 1, and then also if the initial value is 0, then after a long time, the Q is still 0. Understand? So connect, if we connect the two inverters serially, and then the one output is feedback to the input of another inverter, then we can store data. We can store digital signals, which means if the initial value is given, then this initial value is maintained for a long time. It's memory. Okay, we can store some data. We can store digital signals. And then this circuit is called the bistable circuit. Okay? So actually, we can build a bistable circuit like this, but we can draw this bistable circuit like this. It's a cross-coupled inverters. Actually, it's the same. So there are two inputs, Q and Q bar. Okay, and then actually, this is the same equivalent circuit. Okay, this is equivalent circuit, but we just represent the inverters are cross-coupled. Okay, Then if we use this cross-coupled inverters, then we can implement memory. So actually, we do not learn about the memory components, but actually SRAM. So there are two kinds of memory. SRAM can be implemented like this. So actually, the SRAM, the internal memory. So unlike DRAM, our circuit, our chips include the internal memories, but internal memory can be implemented using bistable circuit, like SRAM. Okay, but okay, so actually, uh, if we use the cross-coupled inverters, then we can implement memory circuit. Okay, then what's the problem? So I already explained. So the initial value will be maintained for a long time, consistently. Okay, the maintained. So it's stored. But what's the problem of this bistable circuit? The problem is, so I mentioned that the initial value is maintained. Problem is that we cannot control this initial value. So we don't, so it's actually unknown. So in simulation, it's unknown. The initial value is unknown because there is no input. So we know the signals are stored, signals are maintained, but we cannot control the stored values using bistable circuit. Okay, because so we cannot find any input signals here, right? So no inputs to control the state. We cannot control which data will be stored in this bistable circuit. Then how can we control this memory components, like bistable circuit? So we need to use the latch. So what's the problem? This is the inverter. Inverter has the only one input, into output. But how can we control the output value of this inverter? How? How can we control? So actually, it's not a real bistable circuit, but actually we can find some this feedback loop from out to input. But we want to control this system using input because but in the bistable circuit, this input of inverter is already occupied by output. We cannot use any input for this bistable circuit. It is not possible. So it's a feedback loop and then another input. But this is not possible because we cannot drive. Actually, this node is driven by two driver. It's not possible in a circuit implementation. Then how can we add input to the bistable circuit? I inverter the output is feedback to the input, but we want to control this output. How? We can use basic logic gate, which have two input ports, like the inverter. Which logic? NAND gate or NOR gate. Right. So if we see the NAND gate or NOR gate, this NAND gate or NOR gate includes two inputs, right? And then actually the behavior of this NAND or NOR gate is similar to the inverter, right? Because the output is inversed, right? So which means that we can use one of the input for this NAND gate or NOR gate as this one of the input can receive feedback output, and then one of the input can receive real input signal that can control the output value, right? In the bistable, the bistable circuit does not have any input because inverter does not have any input. Only one input. Okay, so if because and then one input is already occupied by the feedback output, so we cannot control this bistable circuit. But if we use the basic gate like NOR gate or NAND gate, because the output is just inversed, then we can control the output. So we can implement this, we can enhance the bistable circuit like this. And then this circuit is called the SR latch. So, and then you can find the set and reset latch. So, set means it makes out one. Okay, so we frequently use the terminology set or reset in this course, but you can understand that set means that it makes output one. The reset, we frequently use the word reset because we want to, sometimes we need to reset our smartphone, rebooting actually. Reset means the makes output zero. So this is the SR ratio. So S means the set, and then R means the reset. And then also you can find the two input here. So you can find the two outputs here, Q and Q bar, and then we use the NOR gate, right? And then the one of the input of this NOR gate and one is connected to the reset signal. So it means that if R becomes 1, then output will become 0 because this is reset. Make output 0. The set is here. Then if the set is 1, then output will become 1. Okay. Then how can we store data? How can we make this NOR gate like inverter? So if we make NOR gates like inverter, then we can make memory circuit, right? So the bistable circuit is not just a memory circuit. How? If the R is 0 or S is 0, then it's a NOR gate. The one of the input is 0, and then this is in out. Then it is actually equivalent to the inverter. Right. Okay, so which means we can control this circuit, like, and then we can change the values stored in this circuit, and then these stored values can be maintained if we use the NOR gate. NAND gate is the same. We can also implement the SR latch using NAND gate. Okay. So just remember that by stable circuit, you can store data. But in order to control the stored data, we need input and we can implement the extra latch. Okay, so I'll stop here. Any questions? 감사합니다.